As I told you, the transformation of spermatids to sperms is called spermiogenesis. In this process, there is no cell division, no mitosis, no meiosis. Only morphological differentiation occurs. And what is the time taken for this process? It is 12 to 14 days. Mind you, this 12 to 14 days is included in the 72 to 74 days of the total spermatogenesis time. Now we'll see that what parts in the spermatids result in the what parts in the sperms. Now the nuclear material in the spermatid, it leads to the formation of head. The Golgi bodies, they form the acrosomal cap, and the mitochondria, it forms the middle piece, and the tail or the axial filament is formed by the microtubule or the centriole. Now, as in a normal cell, what do you find is lacking in the spermatid? The answer is endoplasmic reticulum, especially the rough endoplasmic reticulum that is lacking in a spermatid. Now we have one more important question, that what is the arrangement of the tail? Now as we know that the tail is formed out of centriole, and this centriole has 9+2 arrangement. So our tail has 9+2 arrangement. Now few important points about the sperm. Now what is the length of the sperm? It is 55 microns. And once a sperm is ejaculated in the female genital tract, for how long is it capable of fertilizing an ovum? And your answer is 48 to 72 hours. That is 2 to 3 days. And these sperm, they attain their motility in the caudal end of the epididymis. Take care of the word motility, because we'll get a question that where does the sperm attain hypermotility, and we'll come to that later on. The sperm attains its motility in the caudal end of the epididymis. And what is the gene involved in it? It is the catsper gene. And the ion involved is the calcium ions. Now these sperms, although they are capable of fertilizing the ovum for 2 to 3 days, but they lose their motility, or the other way, they remain motile only for 12 hours. And these sperms, they are able to reach the ampulla of the tube in 30 minutes. 30 minutes after ejaculation, the sperms are able to reach the ampulla. And why the ampulla? Because it's here that the fertilization occurs. Now we'll discuss what are the hormones supporting spermatogenesis. Now, as in our body, trigger for all the hormonal mechanism starts from the hypothalamus. So it's the same here also. The hypothalamus is triggered and it leads to the release of GnRH, that is the gonadotropin releasing hormone, from the arcuate nucleus of the hypothalamus in a pulsatile fashion. Now these GnRH, it acts on the anterior pituitary and leads to the release of the gonadotropins FSH and LH. Now what is the end organ for these gonadotropins? It is the testis. So this FSH, it has its receptor on the Sertoli cells, and so it acts on the Sertoli cells releasing inhibin B. And the LH, it has its receptor on the Leydig cells and it leads to the release of testosterone. So how do you remember this? L and L. LH receptors on the Leydig cells, and the remaining, that FSH, it has its receptor on the Sertoli cells. Now this inhibin B and this testosterone, they have negative feedback action on the anterior pituitary as well as the hypothalamus, and so they inhibit the release of GnRH and LH and FSH. Now this testosterone, it is the main hormone involved in the spermatogenesis, but LH and FSH, they are the accessory hormones responsible for spermatogenesis. So if your question is the main hormone needed for spermatogenesis, your answer will be testosterone. But If you have an option in which you have testosterone, LH and FSH all, the answer will be more correct. Now few words about the pulsatility of GnRH. Now what is the transmitter involved in the pulsatility of GnRH? It is kisspeptin. And what is the receptor involved? It is KIS-IR receptor. Now few words about this testosterone. Now this testosterone secretion starts at 7 to 8 weeks of the intrauterine life. It starts at 7 to 8 weeks, continues to increase for another 7 to 8 weeks, and so it is the maximum at 15 weeks. That is in the second trimester. Then it decreases and continues at low levels till puberty, that is till the onset of spermatogenesis. Now when does the secretion of testosterone become equivalent to that of an adult male? It is at 17 years of age. And what is this value? It is 5 to 7 milligram per day. Now out of this 5 to 7 milligram, only 0.5 to 3% is the free testosterone, and the rest, it is bound to the sex binding hormone globulin and albumin. Now, how does the secretion of testosterone start in the intrauterine life? It is because the first stimulus for the Leydig cells to release testosterone is not LH. And what is that? It is HCG, human chorionic gonadotrophin. This forms one more important question. That what is the first stimulus for the Leydig cells to release testosterone? And your answer will be HCG. Now this testosterone in males, it is converted into estradiol and dihydrotestosterone. And what are the enzymes involved in this? The testosterone is converted into estrogen by the enzyme aromatase. And where does it occur? The 20% of this aromatization occurs in the testis and the rest in the adipose tissue. And this aromatization converts testosterone into estrogen. And what is the daily production of estrogen? It is 50 microgram per day. Now, why this estrogen is produced in males? It has got certain functions. What are these functions? This estrogen increases the bone mineral density. It causes the closure of the epiphysis of the long bones, helps in body fat maintenance and the sexual functions. Now we told that this testosterone is also converted into dihydrotestosterone. So what is the enzyme involved in that? It is 5-alpha reductase. This 5-alpha reductase converts testosterone into dihydrotestosterone, which is the most potent androgen. Okay? And what is the ratio of testosterone is to dihydrotestosterone? It is 10 to 15 is to 1. See, the most potent androgen less in amount. So, the ratio of testosterone is to